Picking up where we left off in the last video, talking about limit problems. With limit problems, the x value is getting closer and closer to some value. X gets closer and closer to some value, whatever that is, but it never gets there. It never quite gets there. And hopefully you saw that yesterday when we were doing the limit problem. What we're trying to figure out is what happens to the function. I'm sorry. If we try to evaluate that function, or in other words, what happens to f of x when x is equal, oops, if I can write, equal to that value, whatever we're trying to approach here. What happens to the function, or what is that function when x is exactly equal to that value? Has no effect on the limit. And we'll look at some examples of what I mean by that. Has no effect on that limit. So for example, I'm going to give you the same problem that we worked out yesterday, that fraction, but I'm going to make it a piecewise function this time. Let's say I'm going to define f of x as the piecewise function of the fraction that we talked about yesterday, x squared minus x minus 12 all over x minus 4. And that is only when x is not equal to 4. So that's the first piece. And then let's say f of x is equal to 2 when x is equal to 4. So there's a piecewise function. If we wanted to graph that function, the graph would look exactly like the graph looked yesterday, except it would have a hole where x is equal to 4 and y is equal to 7, but then it would go on and on forever. So we have an open circle here for the top part, and the bottom part of this function is f of x is equal to 2. So 2 is right underneath here, so we would have the function equal to 2. So we would have a point defined here at 4, 2. So if I wanted to evaluate f of 4 is actually equal to 2. Right here, that's what the piecewise function says. However, the limit of this function as x approaches 4, the limit of that function is not equal to 2, even though f of 4 is equal to 2. What it is equal to, the limit as x approaches 4 of f of x, is as we're getting really, really, really close to 4 in the x direction from both ways, the y value is getting close to 7. So even though f of 4 is equal to 2, the limit of this function as x approaches 4 is actually equal to 7. So it really doesn't matter what that f of x value is. What we're looking at is the values that this f of x is getting close to as x gets closer and closer to 4 from both directions. So that's just one kind of an introduction for today. Now, the easiest limit problems that we have are continuous functions. This is not continuous. It has a hole in it. A continuous function just continues on without any breaks in it. So the easiest functions to evaluate limits for are continuous functions. In other words, usually they're just polynomials. In other words, this f of x will never be undefined, won't ever be undefined. So for example, let's say we have f of x equaling something simple like 7x minus 3. That's just a continuous function. It's always defined. The input is all real numbers. We are going to use direct substitution to solve limits on this or any continuous function. For example, if I want to find the limit of that f of x function as x approaches 0, let's say, all we have to do, because it's continuous, all we have to do is directly substitute 7 times 0 minus 3, which is negative 3. So the limit of that function as x approaches 0 is equal to negative 3. You can show that numerically, you can show it graphically, analytically, it's already as simple as it can get. Or if you want to do the limit as x approaches 8 of f of x, all we have to do is direct substitution, x equals 8, so 7 times 8 is 56, minus 3 is 53. So that's the easiest type. And sometimes you'll just get a plain old polynomial function. You're going to be asked to find the limit, and you can say, oh, this is always defined. It's never undefined. It's a continuous function. All I have to do is do a direct substitution. Okay, if you don't have a continuous function, you're either going to use numeric or algebraic or graphical methods. They're needed for discontinuous functions. So I'll say NAG, numerically, analytically, or graphically methods are needed for discontinuous functions like fractions or piecewise functions. Okay, because they're undefined at some values. All right, so now what we're going to look at are two different types of limits. We're going to look at right and left-sided limits. Right and left-sided, or in other words, one-sided limits. Okay, one-sided limits. Not all limits exist for some functions. Not all limits exist for some functions, and we'll take a look at one of those where a limit doesn't exist. A limit is said to exist if the y value is the same when x approaches that x value from the greater than and the less than side. A limit is said to exist if the y value is the y value approached, there's our word approached again, the y value approached is the same when x approaches its value that we're evaluating it for from the less than, or in other words, the left side, from the less than, and the right side, or the greater than, and the greater than, or in other words, the right side. And I'm going to give you an example from the table what I mean by that. If you want to go back to the notes that we took on the previous video, we were looking at some numeric values here of this function, x squared minus x minus 12. What we're doing is we're trying to find the limit as x approach 4. So we were looking at the limit as x approach 4 from numbers less than 4 and for numbers greater than 4. So what's happening here is we're closing in on x equals 4 from the right because these are numbers greater than 4. So x is approaching 4 in this direction. You're going to put a little plus sign in here. It means x is getting closer and closer and closer to 4 from the right. Now on this side here, x is getting closer and closer and closer to 4 from the less than side. So we can say x is approaching 4 from the left, or you're going to put a little negative on here. And in the other example here that we had the sine of x over x, we were trying to approach 0 from the negative and the positive. So what we have here is coming in here, x is approaching 0. These numbers are less than 0, so it's from the negative or from the left. And as we're getting closer and closer and closer to 0, x is approaching 0 from the right-hand side. In other words, these x values are greater than 0, but we're getting closer and closer and closer and closer to 0 from the right-hand side. If you wanted to take a look at the graph, what's happening is we're getting closer and closer and closer to 0 from the right. So we're coming in from the right and we're coming in from the left. And as we're getting closer and closer, we're zooming into 0 from the right and from the left. That's what these values mean. So this would be approaching 0 with a little plus. This would be approaching 0 with a little minus, because it's the less than 0, the greater than 0, coming in, zooming in, and approaching that. So let me give you an example of a function where the limit will not exist at a particular value. Example of a function whose limit does not exist. And when we say it does not exist, we can just write that as DNE. DNE is the abbreviation in limits for does not exist. So I'm going to give you just a quick graph of a function. Let's say we have a graph that's coming up like this that ends here and goes to the left forever. And then we have directly underneath it an open circle, and then this graph is going down from here. But this whole thing, this whole graph is called f of x. So this is a piecewise function. And let's say this x value is 3. Let's say this y value up here is, I don't know, a 5. And let's say this y value right here is a 1. So we can evaluate this in many different ways. Let's say we want to find what is f of 3. What that means is when x equals 3, what does y equal? Well, when x equals 3, y equals 5. Right there, because it's the closed-in circle. F of 3 is equal to 5. But now let's get a left-sided limit. Well, the left-sided limit says we're coming in to x equals 3 from the left-hand side, and so we would write it like this. The limit as x approaches 3 with a little minus here. Minus means from the left. The limit of that function means, or you don't have to have double parentheses here, I don't know why I put that, but the limit of that function means what is the y value equal when we're coming in from the left side? Well, the limit here is 5. But if we come in from the right-hand side, if we do a right-sided limit, we're going to write it like this. The limit of f of x as x approaches 3 from the right-hand side, that's the plus up here in this little exponent position, it means what are the y values getting closer and closer to as we're approaching 3 from the right-hand side? Well, these y values are equal to 1. So that limit equals 1. That limit equals 5. And if the function has two different limits, if it has a different left-sided limit as the right-sided limit, it said this overall limit as x approaches 3 does not exist. So we'll write it like this. Since the limit as x approaches 3 from the left-hand side of f of x does not equal the limit as x approaches 3 from the right-hand side of f of x, since they are not equal to each other, 5 does not equal 1, then the limit as x approaches 3, now we don't have to put anything here, the limit as x approaches 3, not left, not right, but both, the limit of f of x does not exist because they're two different numbers. This function has no limit when x equals 3. In other words, this function has no limit when x equals 3. It's discontinuous. There's a gap in this graph at x equals 3, different left and right-sided limits. If this piecewise function actually came together here, it would have a limit because the left and the right would be the same. So what I want you to do now is I want you to try one on your own. So let's see, I want you to, when you write this down, I want you to try it on your own, shut the video off and see if you can get it, and then you can turn the video on again because I'll work it all out. But let's say f of x is equal to this piecewise function. Let's say it's equal to x squared when x is less than 1. And let's say this function is equal to 3x minus 5 when x is greater than or equal to 1. So there's your function. I want you to find 4 things. First of all, I want you to find what is f of 1. We usually look at this is called the breaking point when x is equal to 1. That's where the piecewise function, it either breaks apart like this, or if they actually come together, it's just kind of a place where the two functions they meet each other, but they're not the same function. So try to find f of 1, that should be easy. And then I want you to find the limit of f of x as x approaches 1 from the left. And then I want you to find the limit of this function, f of x, when x approaches 1 from the right-hand side. And then number 4, I want you to find the limit as x approaches 1, neither right or left, of f of x. So find those 4 things, shut the video off for however long it takes you, and then turn it on, and I'll explain what these answers are. And we'll see how much you understand about limits. All right, the first one, f of 1. Well, f of 1, when x is greater than or equal to 1, I'm going to use this piece of the piecewise function. So f of 1 is equal to 3 times 1 minus 5. 3 times 1 minus 5 is equal to negative 2. The limit of this function as x is coming into 1 from the lower. We would be using this branch right here. F of x is equal to x squared. Now something very, very, very close to 1, you can do this numerically if you want or graphically if you want. But you would find is you could just substitute a 1 in for x squared. So the limit of this function when x is getting closer and closer to 1 from the left or from less than, that is equal to positive 1. You can look at the graph if you want. Maybe I'll show you the graph of this. Number 3, what is the limit as x is approaching 1 from greater than, or from the right-hand side? Well, this is the branch that you're going to be using. So that is equal to, you're going to just substitute 3 times 1 minus 5, which is equal to negative 2. And since these two are not equal, since the limit from the left is not equal to the limit from the right, the overall limit does not exist. And then we can take a quick look at this graph, y equals x squared when x is less than 1. So here's a 1. We would have an open circle here. And here's y equals x squared. And then y equals 3x minus 5. Let's see. We'd start at 1, negative 2. Down here we'd have a filled-in circle, and the slope is 3, so it would be kind of a steep one like this. So here's the piecewise function. If we were to graph this, it would look like this. And you can see from the graph as you're approaching 1 from the left, it's a different value as you're approaching 1 from the right. And that's about it for today. This is left and right-hand sided limits and functions where limits do not exist at particular spots. Oh, let's do one more thing. Let's find the limit of this function just for kicks. The limit is of this function as, let's say, x approaches negative 1. What would that be? Well, all we have to do is go to the branch when x is less than 1. It's equal to x squared, which is negative 1 squared, which is equal to 1. And you can see that on the graph. If you have a negative 1 here, the limit of this function when you're coming in from the from the right-hand side of -1 and from the left-hand side of -1, it's equal to +1. So this overall limit does exist, because this would be the same as from the plus side, from the minus side, so it has an overall limit. The only place where it doesn't have an overall limit is at this breaking point in the graph x = 1. And now that's it.